Hi everyone, thank you for taking the time to listen to my presentation today. My name is Wen Fan. I come from the Department of Engineering Mathematics at the University of Bristol. The subject of my presentation is Graph Neural Networks for Interpretable Tactile Sensing. The tactile sensor we used in our research is called the tact tip. Well, the tact tips are a range of biomimetic optical soft tactile sensors, and they are developed by the Bristol Robotics Laboratory. And the tact tips are inspired by the biomimetic principles, that is transducing the deformation on the skin surface via the pin movement. Well, the pins, just like the cells within our human's fingertip. When we use a hand to touch something, the cells within the fingertip can give us the feedback. So this feedback, just like the pins, so the pins can achieve the similar function like the cell. Well, the vision should be the most popular way for the robot to do the recognition and perception. But sometimes the vision-based method may become quite challenging due to the view occlusion or the poor light condition. So tactile perception could be an alternative option for the robot to explore the environment. Our basic target is to apply the tactile sensor into the object classification, and there are 10 different 3D printed objects are used for the data collection. Well, recent years we have seen a lot of amazing results that combine the deep neural networks into the various research areas, especially the convolutional neural networks. The input data of the CNN should be the pixel level data, and it has relatively high resolution, and the trained CNN model have millions of parameters. But as for the tactile sensor, the pins have specific number of the pins, and for example 169 for our research, and it have relatively low feature density. So in this way, we think the CNN is not efficient enough to extract the pin. Well, the graph should be another option. The graph neural networks can be fed as a graph, and the graphs consist of nodes and edges. Well, the pins in our tact tip can be regarded as the graph nodes naturally, and the displacement between the nodes can be identified as the node edges. So we hope to use the graph neural networks to find out the implicit relationship during the deformation. So the first step is how to make the graph representation. The raw image come from the tact tip sensor will be pre-processed, and then use a blob algorithm to extract the pin. And next, we can use the KN method to build the graph edge. We found that the number of k, which should be the parameter for the KN classifier, has significant impact on the graph generating, and in terms of the efficiency, robustness, and connectivity. So we proposed an adaptive KN method to minimize the redundant edge generation between the outermost nodes with their remote neighbors. The framework of our tactile GN model can be seen in this slide. Well, the generated graph consists of two parts, which should be the node and edges, and both of them should be processed by the GCN layer. And GCN means the graph convolutional networks, and it should be the classic and popular layer within the GN model. And the GCN layers could help us to extract the feature maps, and this feature maps will be processed by the polygon layer and fully connected layer to do the classification. Well, to find out the optimal GN model, we conduct the empirical evaluations to find out how the best setting should be. We have tried a variety combinations, including the different layer numbers, different filter numbers, different polygon methods, and beyond that, we also take the physical characteristics of the tact tip into consideration. For example, there are 8 layers of pins within our skin surface, so we think at least 7 layers of GCN are needed to maintain the spatial features. As for the performance of the optimal GN model, it can achieve quite a high level. For example, the 7 layers of GCN can achieve nearly 99% of the accuracy. Well, then we use a grid-count-based method to evaluate the explainability of our result. And the gradient neural network uses a gradient backward to adjust the redundant bias within layer. So if we can visualize the gradient level within each layer, maybe we can find out how the AI predict the result. Well, the grid count is such a method which can achieve that. We apply this method on the CN, and as for the GN, we apply an extra method named the U grid count, and U means the onside. It can indicate both the positive and negative contribution of each node. Well, we found that even after the noisy and the binarization, CN preferred to predict the result based on the background, and that means the attention of the CN can be easily distracted by some small noise. Well, we can refer that if there is no data pre-processed, maybe the CN should be more easily to influenced by the other influence, for example, the poor lighting condition. So the graph neural networks has no such worries, since all the graph nodes and edges come from the skin surface, and that means the GN pay more attention on the deformation area. Also, we have learned the learning patterns of the GN with different depths. As for the one-layer GCN, it can learn the contact direction. As for the three-layer GCN, it can find the rough region of the contact. Well, as for the five-layer GCN, it can pay more attention on the accurate region where the deformation has happened. And also, we have made an interface to show how our system works. And to achieve that, we combine the attention method into our system. We use the convolutional blocked attention module, and it consists of two parts. The first part is the channel attention, the second part is the spatial attention. We hope to use the attention method to force the GN focus on the deformation area, so that there should be no suddenly change during the prediction. And there is a result which can show that how it works. Well, at the upper left side, we can see the raw data come from the tactile sensor, and from the upper right side, there is a U-grid count diagram, and this diagram can indicate the positive and the negative contribute of each node. Well, in the middle level, there is a bar chart, and this bar chart can represent the object classification probability. Well, the contributions of our research include these three parts. The first is that we transform the tactile data into the tactile graph representation. And the second is that we develop an optimal GN model for the object recognition. And the third is that we evaluate the explainability of our proposed model and make a comparison between CN. Well, in the future, we would like to apply our method on the real task, for example, the tactile exploration, and we hope to combine the system with a remote teleoperation based on the haptic device. And we hope the operator use the haptic device to control the robot to explore the environment. And once the tactile sensor contacts the object, the neural networks can provide the prediction, and this prediction can be transferred by the force or the torch by the haptic device, so that the operator can receive that feedback just on their hand. It's quite promising. Thank you for your listening.